Welcome to the Deep Dive, the show where we really try to cut through the noise and get straight to the core of complex topics. Have you ever wished you had a shortcut, like a way to genuinely understand the big ideas, to get those aha moments without just drowning in information?
Yeah, wading through endless jargon.
Exactly. Well, if that sounds familiar, you've definitely come to the right place. Today, we're embarking on a deep dive into the fascinating world of machine learning. It's a field that's not just theory anymore, right? I mean, it's quietly shaping so much of our daily lives. Think about how your streaming service recommends your next binge watch, or how your email sorts spam.
Or even discovering new medicines. Yeah, it's huge.
Right. But beyond the headlines and all the buzz, what is machine learning really? And, how does it actually empower machines to learn?
Well, what's truly fascinating here, I think, is that while machine learning can feel a bit like magic sometimes,
It definitely can.
it's actually built on understandable foundations. So today, we're going to pull back the curtain a bit. Our mission really is to distill the core concepts, show you the different ways machines discover patterns and make decisions.
Okay.
And then we'll tackle some of the practical challenges and, the clever techniques that truly make these systems powerful. Our goal is to give you not just the what, but the profound why it matters in the real world.
So by the end of this deep dive, you won't just understand the jargon, hopefully.
Right.
You'll have a solid blueprint, kind of a mental model of how these intelligent systems operate. You'll be able to confidently navigate conversations about AI and machine learning, and maybe, just maybe, see the world a little differently, through the lens of data.
That's the aim.
Okay, so let's strip away the magic then. Where do we start? It all begins with data, right? That's the first ingredient.
Absolutely. Data is everything.
When we talk about machine learning, it all begins with how we feed information to the machine.
Right.
So what are the fundamental pieces of this data puzzle?
Right. So at the heart of it are two key components, feature vectors and labels.
Okay, feature vectors. What's that?
Think of a feature vector as the structured input for any machine learning task. It's basically just a list of characteristics or attributes. So, for example, if we're building a system to predict house prices, a feature vector for one house might be something like square footage, number of bedrooms, location score, a list of numbers.
Okay.
And every house in your data would have a vector following that exact same structure.
Yeah.
The first number is always square footage, the second is always bedrooms, and so on. Consistency is key.
Gotcha. So it's a consistent way to represent the thing we want to learn about, like a fingerprint almost.
Kind of, yeah, numerical fingerprint. And then there's the second piece, the label.
The label, right?
Yeah.
So that's the answer.
That's the answer we want the machine to learn or predict. So for our house price example, the label would be the actual price of that specific house. Or if we were building, say, a system to detect spam emails, the feature vector might be some representation of the email's content, maybe like the presence or absence of certain words, a bag of words representation.
Right.
And the label would simply be spam or not spam.
So the algorithm's job is to figure out the link between that feature vector, the input, and the label, the output.
Exactly. Learn the relationship, the pattern connecting the two.
Okay, so we have our structured inputs, the feature vectors, and our desired outputs, the labels. Now, how do these machines actually learn from this data? You mentioned different types of learning. Let's start with the most common one, supervised learning.
Right. Supervised learning. This is probably the one most people encounter, even if they don't realize it. It's where the machine learns from a data set where every single example has a clear, correct label.
Like having a teacher.
Exactly like having a teacher or a supervisor providing the answers during training. So you feed the machine, say, thousands of spam emails and thousands of legitimate emails, and crucially, each one is correctly labeled. The algorithm then chews on all that data and learns the patterns, the characteristics that tend to distinguish spam from not spam.
And then it can predict new ones.
Precisely. When a new unseen email comes in, it uses those learned patterns to predict its label. Spam or not spam. This is super common for tasks like predicting cancer probability based on patient features, flagging potentially fraudulent transactions, or, that classic spam detection.
Okay, so supervised learning. Learn from examples where we know the answer.
Got it.
But what happens when there's no clear answer, no label to begin with?
Ah, right. That leads us neatly into unsupervised learning.
Okay.
Here, the dataset consists only of unlabeled examples, just the feature vectors, no answers provided, so there's no teacher this time.
So what's the goal then, if there's no answer to learn?
The goal isn't to predict a specific outcome, but rather to discover hidden structures or patterns within the data itself. It's more about exploration.
Like finding groups.
Exactly. A great example is clustering, where the machine groups similar examples together. Imagine, say, a streaming service wanting to understand its customer base better.
Okay.
Unsupervised learning could automatically group customers into different segments based purely on their viewing habits, even if no one explicitly labeled them beforehand as action fans or documentary lovers or whatever.
I see. So it finds the natural groupings in the data. Any other uses?
Yeah, another big one is dimensionality reduction, which sounds fancy, but it's basically about simplifying complex data by reducing the number of features, the number of columns in your data, while trying your best to keep the important information.
Okay, that makes sense. Finding patterns, reducing complexity. And sometimes, you mentioned we have a mix. Some labeled, some unlabeled.
That's right. That's semi-supervised learning. This often happens in the real world where getting labeled data is expensive or time-consuming.
Like medical images needing expert diagnosis.
Exactly. So you might have a small amount of labeled data, but alongside it, a vast amount of cheaper unlabeled data. The algorithm tries to use both. The hope is that the larger unlabeled data set can still give clues about the overall structure of the data, its probability distribution, and ultimately help build a better predictive model than you could with just the small labeled set alone.
Interesting. Using the unlabeled stuff to boost the learning from the label stuff.
Kinda, yeah. That's the intuition.
Okay, and then there's a fourth type, which sounds quite different. Reinforcement learning. We'll keep this brief, but what's the gist?
Yeah, reinforcement learning is really its own beast, a whole subfield. But the basic idea is you have a machine or an agent learning by interacting with an environment.
Like a game.
Games are a classic example, yeah. The agent perceives its current state, like the position of pieces on a chessboard, takes an action, say, moves a piece, and then receives a reward or maybe a penalty based on that action. Its goal isn't just immediate reward, but to learn a policy, a strategy that maximizes its total long-term reward over many steps. Think of teaching a dog tricks with treats, but way more complex.
So it learns through trial and error, essentially.
A very sophisticated form of trial and error, yes. It's incredibly powerful for sequential decision-making problems, things like training robots to walk, playing complex games like Go or chess at superhuman levels, or even optimizing logistics in a warehouse. But yeah, as our source notes, it's a deep topic, so we're just scratching the surface today.
Understood. So, okay, 4 main types. Supervised, unsupervised, semi-supervised, and reinforcement learning. But no matter the type, the end goal is always the same, right? To produce a model.
Exactly. The output of the learning process is always a model. That model is the distilled knowledge, the learned function, the set of rules or patterns. Whatever form it takes, it's the thing that allows the machine to take a new feature vector and deduce a label, make a prediction, or choose an action.
And the brain that the algorithm built.
You could think of it that way, yeah.
Okay, let's pull back the curtain a bit further then. Let's dive deeper into how one of these actually works. You mentioned supervised learning is common. So let's use support vector machines, SVMs, as an example. How does an SVM actually start learning once it gets all that data?
Right. So first, you've done the hard work, gathered your data, converted your real-world things like emails into those numerical feature vectors we talked about. Maybe that email becomes a huge vector representing thousands of words.
Okay, like a 20,000 dimension vector you mentioned.
Could be, yeah. And you've assigned numerical labels, maybe +1 for spam, -1 for not spam. Once the SVM has all that.
What does it see? How does it process those numbers?
Well, it visualizes each feature vector, each email in our example, as a single point in a high-dimensional space. So if we have 20,000 features, it's literally seeing each email as a point floating in a 20,000 dimensional space, which is impossible for us to imagine, but mathematically.
Well, math works out.
The math works. And the SVM's primary job, its main goal, is to find an imaginary hyperplane, which is just a fancy word for a flat surface, like a line in 2D or a plane in 3D, but in higher dimensions.
Okay, a decision boundary.
Exactly, decision boundary. It wants to draw this hyperplane to separate the points belonging to one class, say the +1 spam points, from the points belonging to the other class, the -1 not spam points.
Okay, so it's drawing a line or a plane or a hyperplane to split the groups. But surely there could be lots of possible lines that separate the two groups, right? How does it pick the best one?
That's the clever part of SVMs. Instead of just finding any old boundary that separates the data, the SVM specifically looks for the hyperplane that creates the widest possible empty street or margin between the two groups of data points.
It's the widest street, so it maximizes the gap.
Precisely. It tries to maximize this margin between the decision boundary and the closest data points from each class. And those closest points, the ones right on the edge of the street, they're called the support vectors. They essentially support or define where that optimal boundary lies.
Ah, hence the name support vector machine.
Exactly. And finding this optimal boundary, this widest margin, is framed as an optimization problem. The algorithm searches for the specific parameters of the hyperplane, its position and orientation, that achieve this maximum margin.
That makes intuitive sense. A wider margin feels safer, more robust, less likely to misclassify something near the boundary.
That's exactly the intuition. A wider margin generally leads to better generalization. But you asked the key question earlier, why does a model trained on past data work on new, unseen data? How can we trust it to generalize?
Yeah, that's the million-dollar question, isn't it?
It really is. The intuition here is largely statistical. If your training data, those emails we labeled, is a reasonably random and representative sample of all possible emails, then new emails, whether they're spam or not spam, are statistically likely to fall into the same general regions in that high-dimensional space as their corresponding training examples.
Because they share similar characteristics, similar features.
Right. So that decision boundary, especially the one with the nice wide margin that the SVM found, will likely still correctly separate these new unseen examples. The model generalizes because it learned the underlying structure and patterns of the data, hopefully, rather than just memorizing the specific training points it saw.
Okay, that makes sense. It's learning the general rule, not just the examples. But what if? What if the data isn't so cleanly separable? What if you can't just draw a straight line or a flat plane to split the span and not slam points, even with a margin? What if they're all mixed up in a more complex, nonlinear way?
Right. This happens all the time in real-world data. Things are messy. And this is where SVMs have another really powerful trick up their sleeve. It's called the kernel trick.
The kernel trick? Okay, this sounds interesting.
It is really interesting. So imagine your data points, maybe just in 2D for simplicity, are scattered such that no single straight line can cleanly separate the pluses from the minuses. Maybe the pluses form a circle around the minuses, or something twisty.
Yeah, you can't draw one line through that.
No, straight line, no. The kernel trick allows the SVM to implicitly, and that's the key word, implicitly, transform this data into a much higher dimensional space. Sometimes even an infinite dimensional space.
Whoa, infinite dimensions, how?
Well, mathematically. The magic is that in this hypothetical higher dimensional space, the data becomes linearly separable. Imagine projecting your tangled 2D points onto a 3D surface where suddenly you can slice through them with a flat plane.
Okay, I can visualize that.
Yeah.
But you said implicitly. So it's not actually creating this massive, maybe infinite dimensional space and putting the points there, because that sounds computationally impossible.
Exactly. That's the genius of the kernel trick. Instead of actually performing that incredibly complex, computationally expensive mapping of every data point to the higher dimension, and then finding the separating hyperplane there,
It finds a shortcut.
it uses a special function called a kernel function. This function calculates the relationships between pairs of points, specifically their dot products, as if they had been mapped to that higher dimensional space. But it does the calculation using only the original lower dimensional feature vectors.
So it gets the benefit of the higher dimension without paying the computational cost.
Precisely. It allows the SVM to find complex, nonlinear decision boundaries in the original space by effectively doing linear separation in a cleverly chosen higher dimensional space without ever explicitly going there. Common kernels, like the RBF kernel, can effectively handle very complex boundaries. It's an incredibly elegant and powerful mathematical shortcut.
Wow, okay, that is a huge aha moment, the kernel trick. That's really clever.
It's one of the reasons SVMs were and still are so influential.
Okay, so we've seen how algorithms like SVMs learn these patterns, find boundaries, even complex ones. But as the person, the analyst or engineer building these systems, what levers do we actually get to pull? You mentioned this distinction earlier, parameters versus hyperparameters. Can you break that down? Why is it important?
Yes, this is absolutely fundamental for anyone actually doing machine learning. So parameters are the values that are learned by the algorithm itself directly from the training data.
Like the SVM finding the exact location and angle of that decision boundary.
Exactly. The specific numbers that define that hyperplane, we often call them weights, W and bias B, those are parameters. The machine discovers these optimal values during the training process, usually by trying to minimize some error or maximize that margin we talked about.
Okay, so the algorithm learns the parameters. Then what are hyperparameters? That's our control panel.
That's a great way to put it. Hyperparameters are settings or properties of the learning algorithm that you, the data analyst or engineer, have to set before the training process even starts.
We choose them up front.
Right. These values directly influence how the algorithm learns and what kind of model it ultimately produces. For an SVM, a classic hyperparameter is that C value, sometimes called the cost parameter. It controls the trade-off between having a wide margin and correctly classifying all the training points. A small c allows more misclassifications for a wider margin. A large C tries harder to classify everything correctly, potentially leading to a narrower margin and overfitting.
I see. So C is like a knob we turn to tell the SVM how much we care about errors on the training data versus getting a smooth boundary.
Exactly. Another example we'll see later is the learning rate for optimization algorithms like gradient descent. The machine doesn't learn the best AC or the best learning rate from the data. You choose them, often through experimentation, based on your understanding of the algorithm, the problem, and the data itself. Getting hyperparameters right is crucial for good performance.
Okay, that distinction is clear. Parameters are learned by the machine. Hyperparameters are set by the human. That seems really important to grasp.
It really is. It dictates where you focus your efforts when building a model.
So how does the machine actually find those parameters, like the optimal W and B for the SVM or the best fit line in other models? You mentioned gradient descent. What is that? Is it an algorithm itself?
Good question. Gradient descent isn't really a machine learning algorithm per se, but rather a foundational optimization algorithm. It's the workhorse engine that many machine learning algorithms use under the hood to find the set of parameters that minimizes their particular error or cost function.
Okay, an optimization engine. How does it work? You used a mountain analogy before.
Yeah, imagine you're standing somewhere on the mountainside, maybe in a thick fog, and your goal is to get to the lowest point, the bottom of the valley. You can't see the whole landscape.
Right, you can only feel the ground right under your feet.
Exactly. So what do? You feel which way the ground slopes down steepest right where you are, and you take a small step in that direction.
Makes sense. Keep going downhill.
That's precisely what gradient descent does. Mathematically, it calculates the gradient, which is basically the direction of the steepest ascent or slope of the error function at the current parameter values. Then it takes a small step in the opposite direction of the gradient, downhill.
And it just keeps doing that, step by step.
It repeats this process iteratively. Calculate the gradient, take a small step downhill, recalculate the gradient at the new spot, take another step, and so on. For something like, say, linear regression where you're trying to fit a line, it would iteratively adjust the slope and intercept of the line, bit by bit, to minimize the average squared difference between the line's predictions and the actual data points.
Until it finds bottom.
Or gets stuck somewhere.
Ideally, until it converges to a minimum point where the slope is basically zero. It might find a local minimum, not necessarily the absolute lowest point globally, but in many ML problems, that's often good enough. And the size of those steps it takes is crucial.
Right. You mentioned the learning rate. That's a hyperparameter. Yes, the learning rate, often denoted by alpha, is a key hyperparameter you set. It controls how big each step is. If the learning rate is too large, you might overshoot the minimum and just bounce around erratically, never settling down.
Okay.
If it's too small, it might take an incredibly long time, thousands or millions of steps to reach the bottom. So finding a good learning rate is part of the tuning process. And there are many variations of gradient descent, like mini-batch SGD, Atom, Adigrad, designed to make it faster and more stable. But the core idea is this iterative downhill stepping.
Got it. So it's the engine driving the parameter search for many ML algorithms.
Yeah.
That clarifies things. Now, this makes me wonder, with all these algorithms like SVMs, gradient descent, kernel tricks, are machine learning engineers actually coding all this stuff from scratch every single time they build a new system?
Oh, almost never. Not in day-to-day practice, unless maybe you're doing very fundamental research, developing a brand new algorithm type.
So what do they use?
In reality, engineers and data scientists rely heavily on incredibly well-built, robust, and highly efficient open-source libraries. In the Python world, which is dominant in ML, libraries like scikit-learn, are indispensable.
Scikit-learn, I've heard of that.
Yeah, it provides stable, optimized implementations of almost all the standard machine learning algorithms we're discussing today. SVMs, linear regression, logistic regression, decision trees, clustering algorithms, you name it.
Yeah.
It also includes tools for things like data splitting, performance evaluation, and more.
So you can just import an SVM and use it.
Pretty much. You import the SVM class, you create an instance of it, maybe you set some hyperparameters like C or the kernel type, and then you call a .fit method with your training data and a .predict method for new data. Swapping out an SVM for, say, logistic regression model might just involve changing 1 or 2 lines of code to import and instantiate the different model.
Wow, that makes things much more practical.
It absolutely does. It allows practitioners to focus less on the intricate implementation details of each algorithm and more on the bigger picture, understanding the problem, preparing the data, choosing the right algorithm, tuning it, and evaluating the results.
Okay, so if they're not spending all their time coding the algorithms, what are they spending most of their time on? You hinted at data preparation earlier.
A huge amount of effort, often the majority of the time and effort in a real-world machine learning project goes into feature engineering.
Feature engineering. Okay.
This is really the art and science, maybe more art than science sometimes, of transforming that raw, messy, real-world data into those clean, informative feature vectors that the algorithms actually need.
Because real data is rarely clean and ready to go.
Oh, never. Think about raw data like customer interaction logs from a website or text from social media posts or sensor readings from a factory floor. It's often inconsistent, has missing values, contains irrelevant information, and isn't in a nice numerical format. Feature engineering is about cleaning that up, selecting the relevant bits, and transforming them into meaningful numerical features that have high predictive power for your target variable.
So it takes creativity and knowing the subject matter.
Absolutely. It requires a lot of creativity, intuition, and often deep domain knowledge. You need to understand the data and the problem to figure out what features might be useful. For example, from raw text, do you just count words? Do you look at sentence length, sentiment, specific phrases? For user logs, do you look at time spent on page, click frequency, purchase history? How do you combine these? It's often an iterative process of trying things out.
Could you give a couple of quick, concrete examples of feature engineering techniques? You mentioned bag of words for text.
Sure. Another very common one is one-hot encoding. Imagine you have a categorical feature like color with possible values red, yellow, green. You can't just assign them numbers 1, 2, 3 because most algorithms would mistakenly assume there's an order, like green is more than red.
Right, that doesn't make sense.
So with one-hot encoding, you convert this single color feature into 3 new binary features. Is red, is yellow, is green. A red item would have the vector 1, 0, 0, yellow 0, 1, 0, and green 0, 0, 1. Now there's no implied order.
Okay, that makes sense. Turning categories into numbers without messing things up. What else?
Another big one is normalization or standardization for numerical features. Let's say you have age, ranging from 0 to 100, and income, ranging from 0 to millions. If you feed these directly into an algorithm like SVM or anything using gradient descent,
the income feature would dominate because the numbers are so much bigger.
Exactly. The scale difference can cause problems. The features with larger values might dominate the distance calculations or the gradient updates, making the algorithm slow to converge or overly sensitive to those features. So normalization typically rescales features to a fixed range, often 0, 1. Standardization rescales them to have a mean of 0 and a standard deviation of 1. This puts all features on a comparable scale, which usually helps algorithms learn faster and perform better.
Okay, rescaling things to be on a level playing field. And what about gaffes in the data? Missing values. That must happen all the time.
All the time. It's a very common headache. Dealing with missing features is a critical part of feature engineering. There are several strategies.
Like what? Just throwing out the data.
You can simply remove examples that have missing values, especially if you have a lot of data and only a few are missing. Or you could remove the entire feature column if it has too many missing values and maybe isn't that important.
But if you want to keep the data,
then you need data imputation. This means filling in the missing values. The simplest way is to replace missing values in a column with the mean or median of that column.
Okay, just guessing based on the average.
Right. It's often better than nothing. More sophisticated techniques might involve using other features in that same data point to predict what the missing value might be, essentially, building a small model just to fill in the gaps in another feature. The best approach really depends on the data and the problem.
Wow, okay. Feature engineering sounds like where a lot of the real craft lies.
It absolutely is. Often, clever feature engineering makes a bigger difference to model performance than choosing a slightly different algorithm. Garbage in, garbage out applies strongly here. Good features are crucial.
So let's say we've done all this hard work. We've gathered the data, cleaned it, engineered amazing features. Everything's numerical and ready. What's the next really critical step before we finally train our model?
Okay, this is arguably one of the single most crucial steps in the entire supervised learning workflow. Splitting your precious labeled data into 3 distinct sets.
3 sets, not just one.
3 distinct sets: the training set, the validation set, and the test set.
Okay, train, validation, test. What's each one for?
The training set is usually the largest chunk, maybe 60–80% of your data. This is the data the algorithm actually learns from. It's used to build the model to find those parameters we talked about, like the SVMs hyperplane.
Okay, that's where the learning happens. What about the validation set?
The validation set, sometimes called the development set or dev set, is a smaller portion, maybe 10–20%. Its crucial role is to help you choose the best learning algorithm, and importantly, to tune those hyperparameters we discussed earlier.
Ah, so you try different C values for your SVM or different learning rates and see which one performs best on the validation set.
Exactly. You train models with different hyperparameter settings on the training set, and then you evaluate each of those trained models on the validation set. The settings that give the best performance on the validation set are the ones you choose.
Okay, and then the test set, what's left for that?
The test set, again, maybe 10–20%, is held back completely untouched during the training and tuning process. You only use it once, right at the very end, after you've chosen your final model and hyperparameters using the training and validation sets. The test set provides the final, unbiased assessment of your model's performance on truly unseen data. It tells you how well you can expect your model to generalize to the real world before you actually deploy it.
Okay, wait. Why do we need 3 sets? Why not just split into training and test and use the test set to tune the hyperparameters? Seems simpler.
But that's a dangerous trap. This is fundamental. If you use the test set repeatedly to guide your decisions, whether it's choosing between algorithms or tuning hyperparameters, you are essentially leaking information from the test set into your model selection process.
Leaking information.
Oh, because you're optimizing your choices based on what works best on that specific test set. Your model might end up performing well on that test set simply because you tuned it to do so, but it might not generalize well to genuinely new data it has never encountered in any way before. You've inadvertently overfit to your test set.
Oh, I see. So you're basically using the test set as part of the learning process, even if indirectly.
Exactly. The test set loses its power as an unbiased estimator of real-world performance. By having a separate validation set for all the tuning and model selection, you keep the test set pristine, truly held out until the very final evaluation. This gives you a much more honest assessment of how well your model is likely to perform when deployed. It's crucial for avoiding building a model that looks great in development but fails in practice.
Okay, that makes perfect sense now. Train on training, tune on validation, final check on test. Never touch the test set until the absolute end.
That's the golden rule. It helps combat that dreaded problem.
Yeah.
Overfitting.
Right. Overfitting and underfitting. We touched on this, but let's define them clearly. You just mentioned overfitting the model learns the training data too well, including noise. What's underfitting again?
Underfitting is kind of the opposite problem. It's also known as having high bias. This happens when your model is too simple to capture the underlying patterns in the data. Maybe you're using a linear model when the relationship is clearly curved, or maybe your features just aren't informative enough.
So it performs poorly everywhere.
Pretty much. An underfit model typically has high error on the training data itself, and it also won't generalize well to new data because it hasn't even learned the basic patterns from the training set. It's just too simple for the job.
Like trying to draw a straight line through a squiggle.
Exactly. And overfitting, then, is also known as high variance. This happens when your model is too complex. It learns the training data too well.
How could it be too good?
It starts modeling not just the underlying patterns, the signal, but also the random noise and the specific idiosyncrasies of that particular training set. It essentially memorizes the training examples.
Okay.
So it might achieve near perfect accuracy on the training data it saw, but because it learned the noise, it fails to generalize to new unseen data. Its performance drops significantly on the validation or test set. It's too sensitive to the specific training data, change the training data slightly, and you might get a wildly different overfit model.
Right, like drawing a ridiculously curvy line that hits every single training point perfectly, but but then makes crazy predictions for points in between.
That's a perfect analogy.
So overfitting seems like a really common and tricky problem, especially with complex models like deep neural networks, potentially.
Yeah.
How do we fight it? How do we encourage the model to learn the signal, not the noise?
The main weapon against overfitting is regularization.
Regularization. Okay, what does that involve?
Regularization is really an umbrella term for a collection of techniques that basically force the learning algorithm to build a simpler, less complex model. The core idea is to add a penalty term to the algorithm's objective function, the thing it's trying to minimize, like error. This penalty discourages the model parameters, like the weights W in SVM or regression, from becoming too large.
Why does penalizing large weights help?
Generally, models with smaller weights tend to be simpler and less sensitive to small changes in the input features. Overfit models often have very large weights as they try to precisely fit every little wiggle in the training data. By adding a penalty for large weights, regularization encourages the algorithm to find a solution that still fits the data reasonably well, but with smaller, smoother weights, leading to a less complex model.
So it's like putting the brakes on the model's complexity.
Exactly. It's deliberately making the model slightly less perfect on the training data in the hope of making it perform better on unseen data. Common types are L1, lasso, and L2, ridge regularization, which add different kinds of penalties based on the size of the weights.
And this relates to that bias variance thing.
Yes, perfectly. Regularization typically increases the bias slightly because the model becomes simpler and might not fit the training data quite as perfectly, but significantly reduces the variance, making it less sensitive to the specific training set and better at generalizing. It's all about finding the sweet spot in this bias-variance trade-off to get the best overall performance on unseen data.
Got it. Find that balance. Okay, so we've built our model, maybe used regularization, we've used our validation set to tune hyperparameters. Now we bring out that pristine test set. How do we actually measure how good the model is? How do we assess performance?
Right, the final evaluation. It depends on the type of problem. For regression models, the ones predicting a continuous number like a house price.
We use mean squared error.
Mean squared error, MSE, is the most common, yes. You calculate the difference between the model's prediction and the actual value for each example in the test set, square those differences to avoid negatives canceling out positives and to penalize larger errors more, and then average them. Lower MSE is better.
And how do we spot overfitting here?
You compare the MSE on the test set to the MSE you got on the training set, calculated during development. If the test MSE is substantially higher than the training MSE, that's a classic sign of overfitting. The model learned the training data well, but isn't generalizing.
Okay, that's pretty straightforward for regression. But for classification models, spam, not spam, cat, dog, panther, it gets a bit more nuanced, right?
Yeah.
MSE doesn't really apply directly.
Correct. For classification, we often start with the confusion matrix.
Right, you mentioned that. The table showing the different kinds of correct and incorrect predictions.
Exactly. It gives you a much clearer picture than just a single accuracy number. It breaks down the performance into 4 key categories. True positives, TP. The model correctly predicted positive, in the Z, correctly identified spam. False positives, FP. The model incorrectly predicted positive, e.g. called normal email spam, sometimes called a type I error. True negatives, APN. The model correctly predicted negative, e.g. correctly identified a normal email. False negatives, FN. The model incorrectly predicted negative, e.g. missed a spam email, letting it through type 2 error.
Okay, TP, FP, TN, FN. And from this matrix, we calculate metrics like precision and recall. Remind us what they measure again.
Sure. Precision answers the question. Of all the times the model predicted positive, AG said spam, what fraction were actually positive? So it's a TP, TP plus FP. High precision means when the model says something is positive, it's usually right. You minimize the false positives.
Okay, so for spam, high precision means you don't accidentally flag important emails as spam too often.
Exactly, which is often very important. Then there's recall, also called sensitivity or true positive rate. It answers. Of all the actual positive examples that existed in the data, what fraction did the model correctly identify? So it's TP, TP plus FN. High recall means the model finds most of the actual positive cases. You minimize the false negatives.
So for spam, high recall means you'd catch most of the actual spam messages, even if you occasionally flag a good one by mistake.
Right. And as you can probably see, there's often a trade-off between precision and recall.
How so?
Well, if you make your spam filter extremely aggressive to catch absolutely everything, maximize recall, you'll inevitably start flagging more legitimate emails too, lowering precision. Conversely, if you make it very cautious to avoid any false positives, maximize precision, you'll likely miss some actual spam, lowering recall.
So you often have to choose which one is more important for your specific application.
Exactly. Or find a balance. In medical diagnosis for a serious disease, you'd probably prioritize extremely high recall. You want to catch every potential case, even if it leads to more false alarms, lower precision, needing follow-up tests. For something like recommending YouTube videos, maybe precision is more important. You don't want to recommend completely irrelevant stuff, even if you miss some potentially good recommendations, lower recall. You can often tune a model's decision threshold, a hyperparameter effectively, to favor one over the other.
Okay, that makes the trade-off clear. What about just plain accuracy? The total number of correct predictions divided by everything. Isn't that useful?
Accuracy can be useful, but it can also be very misleading, especially when you have imbalanced data sets.
Imbalanced, meaning one class is much rarer than the other.
Exactly. Think about detecting a rare disease or fraudulent credit card transactions. Maybe only 0.1% of cases are positive. A model that simply always predicts negative, no disease, no fraud, will achieve 99.9% accuracy.
Wow. But it's completely useless.
Utterly useless for the actual task. It hasn't learned anything. In such cases, precision and recall, or related metrics like the F1 score, which combines them, give you a much better picture of the model's actual performance on the rare positive class, which is usually the one you care most about. So, always be careful with accuracy, especially if your classes aren't roughly balanced.
That's a really important warning. Accuracy isn't always the whole story. Are there other ways to assess classifiers, maybe ones that handle that threshold tuning aspect?
Yes, a very powerful tool, especially for classifiers that output a probability or a confidence score, not just a hard label, is the ROC curve and its associated AUC value.
ROC. What's that stand for?
Receiver operating characteristic. It's a historical name from signal detection theory, but what it does is plot the true positive rate, recall, on the y-axis against the false positive rate, which is FP plus TN, on the x-axis, for all possible settings of the decision threshold.
Okay, so it shows the trade-off across all thresholds.
Exactly, you get a curve. A random classifier would produce a diagonal line from 0, 0 to a 1. A perfect classifier would go straight up the y-axis to a 1, and then straight across to level 1. A good classifier will have a curve that bows up towards the top left corner.
And the AUC?
The AUC is the area under that curve. It gives you a single number summarizing the classifier's performance across all thresholds. An AUC of 0.5 is random guessing. An AUC of 1.0 is perfect classification. The higher the AUC, closer to 1, the better the model is at distinguishing between the positive and negative classes, regardless of which specific threshold you choose. It's a very common and robust metric, especially useful for comparing different models and less sensitive to class imbalance and accuracy.
Okay, ROC and AUC. Powerful tools for understanding classifier performance beyond simple accuracy. Got it.
Definitely worth knowing about.
All right, let's shift gears a bit now and dive into the really exciting and maybe sometimes hyped area of neural networks and deep learning. You hinted earlier that even simple logistic regression could be seen as a tiny neural network. How do we build up from there?
Yeah, that's a good starting point. Logistic regression takes inputs, multiplies them by weights, adds a bias, and then passes that result through a sigmoid function to get a probability. You can visualize that as a single computation unit or neuron.
Okay, one neuron.
Now, a neural network essentially connects many of these units together in layers. It's basically a series of nested functions. The output of one layer becomes the input to the next layer.
So layers of these calculations.
Right. Typically, each layer performs two main operations. First, a linear transformation. It takes the inputs from the previous layer, multiplies them by a set of learnable weights, and adds learnable biases, very much like linear or logistic regression.
At a weighted sum.
Then, crucially, the result of that linear step is passed through a nonlinear activation function.
Ah, the nonlinearity again. Why is that so important here?
It's absolutely vital. If you just stacked a bunch of purely linear layers, no matter how many you stacked, the entire network would still just be performing one big linear transformation. It couldn't learn complex nonlinear patterns in the data.
It would just be like one big linear regression model.
Exactly. The activation functions, common ones are RealU, rectified linear unit, sigmoid, ton, introduce nonlinearity at each layer. This allows the network, by combining these nonlinear steps across multiple layers, to approximate incredibly complex, wiggly, nonlinear functions and decision boundaries. That's where their power comes from.
And the network learns the weights and biases for all these connections.
Yes, all those internal parameters, the weights and biases in every layer, are typically learned using gradient descent, or more often, sophisticated variants of it like Atom, optimized for large networks. The algorithm adjusts the parameters iteratively to minimize the difference between the network's output and the desired labels in the training data.
Okay, so that's a neural network. Layers of linear transforms followed by nonlinear activations. When does it become deep learning? Is it just about having lots of layers?
That's basically the definition, yes. Deep learning generally refers to training neural networks that have more than two layers between the input and the output. These intermediate layers are often called hidden layers.
So input layer, maybe several hidden layers, then the output layer.
Right. Having multiple hidden layers allows the network to learn a hierarchy of features. Early layers might learn simple features, like edges or corners in an image. Middle layers might combine those to learn more complex features, like textures or simple shapes. And later layers might combine those to recognize objects or complex patterns.
That sounds powerful. Was it always easy to train these deep networks?
Oh, not at all. For a long time, training deep networks was extremely difficult. There were major theoretical and practical hurdles. One huge problem was the vanishing gradient problem.
Vanishing gradients.
Yeah. Remember, gradient descent relies on calculating the gradient, the error signal, and passing it backward through the network layers to update the weights. In very deep networks, especially those using activation functions like sigmoid, these gradients could become incredibly tiny as they were propagated backward.
So the signal faded out.
Exactly. By the time the gradient signal reached the early layers of the network, it was practically zero. This meant the weights in those crucial early layers weren't getting updated, and the network simply failed to learn effectively. There was also the opposite problem, exploding gradients, where they could become huge and unstable.
So how was this solved? What enabled the deep learning revolution we see today?
Several key breakthroughs came together. One was the widespread adoption of activation functions like ReLU, which doesn't saturate and kill gradients for positive values like sigmoid does. Another was the development of better weight initialization techniques. Smarter optimization algorithms like Atom also helped manage gradients better. And for specific types of networks dealing with sequences, specialized gated units like LSTMs and GRUs were invented to explicitly combat vanishing gradients. Plus, of course, much more powerful computing hardware, especially GPUs, and larger datasets became available.
Okay, so deep learning today isn't just about the number of layers, but really about using this modern toolkit, better activations, optimizers, architectures, hardware, data, to effectively train these deep hierarchical models.
That's a great way to summarize it. It's the effective application of this whole suite of techniques.
This has been an absolutely incredible journey through the core mechanics, the practicalities, and even into the depths of neural networks. But before we wrap up, there are a couple of advanced concepts that seem almost like science fiction, but are really powerful in practice. One you mentioned that really blew my mind was self-supervised learning, particularly for word embeddings. How on earth do machines learn the meaning of words without a dictionary?
Right. It is mind-bending, but it's also one of the most impactful breakthroughs in natural language processing, and a fantastic example of leveraging unlabeled data in a clever way. So word embeddings are essentially feature vectors for words, like our feature vectors for houses or emails, but now each word gets its own vector, usually a few hundred dimensions long.
Okay, a vector for every word. What's special about them?
The magic is that words with similar meanings end up having similar vectors in this high-dimensional space. Similar usually means their vectors point in roughly the same direction or are close together. So the vector for Paris might be close to the vector for Rome, and the vector for king might be related to queen in a specific way.
How? How does it learn these similarities without being told Paris and Rome are capitals?
This is the self-supervised aha moment. These embeddings are learned purely from vast amounts of unlabeled text, like scraping Wikipedia or huge web crawls. The trick is the learning task they set up. Models like Word2Vec, specifically algorithms like skipgram or CBOW, don't try to predict a label. Instead, they predict context.
Predict context.
Yeah. For example, the skipgram model takes a word, say learning, from our earlier example, I almost finished reading the on machine learning, and tries to predict the words that are likely to appear nearby in the sentence, like book, article, the, on. It uses the surrounding words as makeshift labels.
Ah, so it's learning. What words tend to hang out with the word learning?
Exactly. By doing this prediction task millions or billions of times across a massive text corpus, the model adjusts the vector for learning. and all other words, so that words that frequently appear in similar contexts end up with similar vectors. It learns that book and article often appear near reading, so that their vectors become similar. It learns meaning purely from distributional patterns, how words are used together.
That is genuinely incredible. It's like emergent intelligence learning semantics just by observing usage. And you mentioned it captures relationships like king minus man plus woman equals queen.
Yes, astonishingly, these vector spaces often capture analogies like that through simple vector arithmetic. The vector difference between king and man is very similar to the vector difference between queen and woman. It learned these relationships implicitly just from the text.
Wow. Self-supervised learning. Learning meaning from context. Okay, that's one mind bender. Another one that sounds like a superpower is transfer learning, especially with these deep networks. What's that about?
Transfer learning is another huge practical advantage, particularly for deep learning models. The core idea is incredibly powerful. You don't always have to train a massive model from scratch for your specific task, especially if you don't have a huge amount of labeled data for it.
So you reuse something that already exists.
Precisely. You take a deep neural network model that has already been pre-trained on a massive general data set, maybe a model like ResNet or VGG trained on the ImageNet dataset, which has millions of labeled images across thousands of categories, like different kinds of animals, objects, vehicles, etc. This pre-trained model has already learned a lot about the visual world.
It learned those general features you mentioned, edges, textures, shapes.
Exactly. Its early and middle layers have become excellent general-purpose feature extractors for images. So for your specific task, maybe you want to classify different types of domestic animals, and you only have a few thousand labeled pictures you take that pre-trained network. You typically chop off its final layer or layers, which were specific to the original ImageNet classification task. Then you add on one or more new layers at the end designed for your specific number of classes. For example, cat, dog, hamster.
And then you train the whole thing again on your small data set.
Usually you don't even need to train the whole thing. You often freeze the weights of the early pre-trained layers, assuming they already know how to see basic features, and you only train the weights of the new layers you added at the end, using your smaller, specific data set.
Ah, so you're just fine-tuning the very end of the network for your task, leveraging all the general knowledge learned from the massive data set.
Exactly. This allows you to achieve surprisingly high performance on your specific task, often much better than training a smaller network from scratch on only your limited data, and you can do it much, much faster. It's like giving your model a huge head start by transferring knowledge from a related domain. It's a complete game changer for applying deep learning effectively in situations with limited labeled data.
Transfer learning. Reusing knowledge. That sounds incredibly efficient and powerful.
It really is. It's democratized access to high-performing deep learning models for many applications.
So wow, what does this all mean for you listening? We've journeyed quite a distance today. We went from the basic building blocks, feature vectors, and labels through the main types of learning. Supervised, unsupervised, semi-supervised reinforcement.
We unpacked how algorithms like SVMs work, finding those decision boundaries, and using really clever ideas like the kernel trick to handle complex data.
Right, and we demystified the practical side, the absolute necessity of feature engineering, the crucial discipline of splitting data into training, validation, and test sets to avoid pitfalls like overfitting.
And how regularization helps find that sweet spot in the bias-variance trade-off. We also looked at how to actually assess performance, moving beyond simple accuracy with things like precision, recall, and the ROC curve.
And then we peeked into the world of deep learning neural networks, activation functions, the challenges like vanishing gradients, and the breakthroughs that power modern AI. We even touched on incredible concepts like machines learning the meaning of words just from context using self-supervision.
And leveraging vast pre-existing knowledge through transfer learning. It's a huge landscape.
It really is. Which I guess raises an important question as we wrap up. Our deep dive has shown that machine learning, at its core, is about turning data into useful predictions, useful insights. But there's that famous quote from the statistician George Box.
Ah, yes. All models are wrong, but some are useful. A classic. And profoundly true in machine learning.
Exactly. So the true power, it seems, lies not just in building a model that gets a high score on some metric, but in deeply understanding its strengths, its limitations, and critically, how it generates its usefulness for the specific problem you're trying to solve, knowing why it works and when it might not work.
Precisely. It's about wielding these powerful tools responsibly and effectively.
So now that you have this blueprint, this framework for understanding how machine learning works under the hood, what new useful models will you start to envision? What problems out there, maybe problems you encounter every day, will you start looking at with a fresh machine learning informed perspective? Something to think about.
Definitely.
Thank you so much for joining us on this deep dive today. We really hope it provided some clarity and maybe sparked some new ideas.
Yeah.
We look forward to exploring other fascinating topic with you soon.